Okay, I just saw this message from Mr. Farrell. So let me make sure I have him down. Okay, so as I was saying, I'm just going to start it off discussing this important fundamental topic in chemistry. Pretty much, you cannot do any chemistry from now on into the future unless you master this particular area, which deals with stoichiometry. And stoichiometry is basically that area of chemistry which deals with the quantitative relationships between substances involved in a chemical reaction. So some of the things that we have learned before, all of them will come into play in this particular chapter. The mole concept will be very important when it comes to this particular topic. Balancing equations, very important. In fact, you cannot solve any problems in this particular topic without working with a balanced equation. In some cases, the balanced equation will be given. In other cases, you'll be given information, and based on that, you're to determine the equation and balance it, right? So what you're going to see is that things that we've learned in previous chapters will come into play in this chapter. So let's review a couple of things that we learned before. We talked about the molar mass, which you can get for an atom, for an element, from the periodic table. Numerically, it's the same thing as the atomic mass. The only difference is the units, whereas the atomic mass is expressed in AMU units, molar mass is expressed in grams per mole, all right? And of course, we know what a mole represents, right? What Avogadro's number for a particular item, it could be atoms, it could be molecules, it could be ions. It's a large number here, 6.02 times 10 to the 23, all right? And of course, when it comes to compounds, the molar mass would be the sum of the molar mass of all the elements that are in the compound based on the formula, all right? So we know the relationship between the molar mass, the mass in grams, and the moles, right? That's a relationship right here. And that's true for an element, and that's true pretty much for any substance, right? Compound, etc. All right? And of course, we know the relationship between Avogadro's number and the moles, which is given by this expression right here, right? So we know the relationship between Avogadro's number and the moles and the molar mass. We have that relationship, which we talked about earlier. So what we'll be looking at, as I said before, are the quantitative relationships that exist between substances involved in a chemical reaction. And the key thing, which I said earlier, and I'm going to say it again, I will not stop saying it, because you simply cannot solve these problems without having a balanced equation, right? So the equation that you're dealing with, if you're solving a problem of the type that we're going to get into, you have to start off with a balanced equation, right? So I think we looked at this example already. That equation, as you see there on the screen, is not balanced. So of course, by now, we all should know how to do that, especially since you have done the assignments, was it 6 and 7 or 7 and 8? I don't remember, but you got a lot of practice in terms of balancing equations, right? So that's how that equation is balanced. And the key thing and the reason why the equation must be balanced is because these coefficients that exist before the different substances will represent the mole relationships between the different substances. So one could look at this reaction and say 2 atoms of aluminum will react with 1 formula unit of iron 3 oxide to form 2 atoms of iron and 1 formula unit of aluminum oxide. But we can also extend that to the mole relationships, right? In other words, the way we can interpret this equation is that 2 moles of aluminum will react with 1 mole of iron 3 oxide to give you 2 moles of iron and 1 mole of aluminum oxide. So the coefficients here not only gives you the relationship between the substances at the microscopic levels of atoms or ions or whatever, but also at the macroscopic level in terms of mole relationships, all right? And that's a key thing that you can garner from a balanced equation, which can help you to solve these problems, all right? Okay, so that's what stoichiometry is all about. I mentioned it before. It deals with the relationships, the quantitative relationships between the different substances in a balanced equation. And one key thing that you're going to be using a lot when it comes to solving these problems is what we call the mole ratio, which is established by the coefficients of the substances involved in the chemical reaction, right? So as stated here, the coefficients used in the mole ratio are derived from the coefficients used in the balanced equation. So again, this underscores the importance of having a balanced equation to begin with. So for example, let's look at this reaction. The reaction between nitrogen and hydrogen to form ammonia. The equation is already balanced, so therefore we can write down the mole relationships between the different substances involved, right? 1 mole of nitrogen reacting with 3 moles of hydrogen to form 2 moles of ammonia. So we can write down, for example, what we call a conversion factor, which represents the mole ratio between two substances, in this case, between nitrogen and hydrogen, right? So it's 1 mole of nitrogen reacting with 3 moles of hydrogen. So we can write down that relationship as a fraction where we have 1 mole of nitrogen above and 3 moles of hydrogen below. But we can also have it the other way around, right? We can have the 3 moles of hydrogen above as a numerator and 1 mole of nitrogen below as the denominator. So you can have for each relationship between any two substances in a balanced equation, we can have 2 conversion factors. And the one that you're going to use is dependent on the type of problem that you're trying to solve, right? So that's the relationship between nitrogen and hydrogen. And just, for kicks, we are showing you the relationship between hydrogen and ammonia, 3 moles of hydrogen to 2 moles of ammonia. In this case, the moles of hydrogen is above here as the numerator, and the moles of ammonia is down here as a denominator. But again, you can have it flipped around. Again, it depends on the type of calculation that you're trying to achieve, all right? So as stated here, the mole ratio is used to convert the number of moles of one substance to the corresponding number of moles of another substance in a stoichiometric problem. The mole ratio is used in a solution of every type of stoichiometric problem. And this goes back to what I said earlier. You need to have a balanced equation because the balanced equation would give you the mole ratio, the correct mole ratio, which you can use to further solve your stoichiometric problem, right? So basically, the mole ratio method involved in solving these kind of problems is basically a stepwise process. The first of which is, if necessary, you convert the amount of substance into moles, right? So for example, if you're given, let's say, one substance involved in a reaction, and let's say that it's expressed or given in terms of grams, then you'd have to convert that to moles, all right? Now, in some question, they probably give you the moles already, in which case you don't need to do this first step. But if you need to, then you'd have to do this first step. If you're given the mass of the substance in grams, or if you're given a quantity expressed in some other measurement, you have to somehow find a way of converting that value to the equivalent mole value. And then step number 2 is where you convert the moles of the starting substance to the moles of the desired substance. So the substance that they're referring to as a starting substance is the substance that you're given information about, or the substance you have determined the number of moles of from step number 1. And then the desired substance is the one that you're trying to find out the mole value of. And of course, you're going to use the mole ratio from the balanced equation in order to do that. And then, again, if necessary, you may need to convert the moles of the other substance into the units specified in the problem. So for example, if the question says you have to convert from, you want to find the grams of the other substance, then you have to convert the mole value that you calculated from step 2 to grams, all right? And we all know how to do that, and we're going to see some more examples of that shortly. All right, so basically, as we said before in step 1, if you're given a mass in grams, you have to multiply by this conversion factor to convert it to moles. 1 mole of the substance divided by the molar mass. And of course, the molar mass you can get from the periodic table, right? So this is just a quick example, a bit of a review of previous chapters. Question says, how many moles of sodium chloride are present in 292.215 grams of sodium chloride? So that's very easy. And what makes it easier is that they gave us the molar mass already. So you did not even have to calculate that, right? If you are not given this, but you're given a formula, then you'd have to go to the periodic table and add up the molar masses of the sodium and the chlorine, and that will give you this number. But fortunately for us, they gave us the molar mass here, and it's very simple. You take the mass in grams, and then you multiply by 1 mole of sodium chloride divided by the molar mass, which is 58.433 grams. and whatever that gives, that would be the answer. So that's 292.215 divided by 58.433. So according to my calculations, rounded off to 5 sig figs. 5 sig figs? Yes, 5 sig figs. 5.0009 moles. And that is it. All right. So that's basically how you do that conversion. All right. As I said before, in some cases, this would be a necessary first step if you're given a mass in grams of one substance in the problem to begin with. Okay, the next step, as we said before, is to determine the mole ratio of the desired substance to the starting substance. And this is based on the balanced equation, right? So the way you'd set this up, let me just skip all this here, is something looking like this, where you have the moles of the starting substance and you multiply by the conversion factor. You have the moles of the starting substance based on the equation, the coefficient in the equation, and up here, so that will be down here, and then up here, as a numerator, the moles of the desired substance, again, based on the coefficient of that substance in the balanced equation. All right. And then, okay, so let's look at this example. So in this particular question, they already gave us a balanced equation, which makes life a bit easier for us. And they said here in this question, or they're asking, how many moles of lead 2 chloride, which is this right here, are formed if 5.000 moles of sodium chloride react? So basically, you're going to start off with 5.000 moles of NaCl. And the question now becomes, what's the conversion factor that you're going to multiply that by? Because you're given the moles of this, and you're asked for the moles of this, all right? So basically what you'd have to do is look at the coefficients for both the sodium and the sodium chloride, that is, and the lead 2 chloride. So of course, we all know that there's a 1 here. Sorry, there's a 1 here. It's understood to be a 1 right there. So therefore, the way you're going to set this up here is that you're going to have 2 moles of sodium chloride down here and 1 mole of lead 2 chloride above. And that's it. And then you do the number crunching, which I can do without a calculator here. And the answer becomes 2.500 moles of lead 2 chloride. And that's it. All right. So again, I'm going to say this over. You'll probably get sick of me saying this over and over again. This underscores the importance of having a balanced equation. Because if the equation is not balanced, then the number that you, or the numbers that you use here in the conversion factor to convert from the moles of one substance to the moles of another substance could be incorrect, right? So whenever you get a stoichiometric type problem, the first thing you should do is have a balanced equation to work with. Either the equation is given to you, or you have to figure out the balanced equation, but you must start off with a balanced equation. Okay, any questions about this example? Any questions? Including you guys out there in Zoom. Any questions? Okay, so in some cases, depending again on how the question is worded, after you calculate the moles of the desired substance, then you'd have to convert to grams or whatever the question is asking for. It all depends on how the question is worded. And we're going to look at some examples, including the questions in the assignments that assignment number 9, which I have for you today, right? So of course, by now you all should know how to do that. If you're asked for the answer in grams, then you take the moles and multiply by the corresponding molar mass. If you're asked, so like for example, in this case here, let's say you worked out that you end up with 5 moles of water, then to convert it to grams, you multiply by this conversion factor, which represents the molar mass of water, right? In some cases, you might be asked for something like the number of atoms or molecules, in which case you need to multiply the moles of the particular substance by Avogadro's number, all right, as you can see in this example right here, all right? In some cases, well, let me see what is, in some cases, you may be asked to convert from moles to molecules, which again would involve Avogadro's number, as you can see in this particular example right here. Okay, so let's look at some examples here. I'm going to skip all this. This is some fluff information. But this is the equation that we'll be working with to solve the problem that is coming up, right? So this equation is already balanced. And the question is asking here, calculate the number of moles of phosphoric acid, which is H3PO4, formed by the reaction of 10.0 moles of sulfuric acid, which is H2SO4. So basically, you're given 10.0 moles of H2SO4, and you're asked to determine the equivalent moles of H3PO4. All right? So first thing we will do is start off with the 10.0 moles of H2SO4. And then you're going to multiply by the corresponding conversion factor, which relates the coefficients of sulfuric acid and phosphoric acid to each other. So based on the balance equation, for every 3 moles of phosphoric acid produced, 5 moles of sulfuric acid will react. So the question now becomes, what goes up here as the numerator, and what goes down here as the denominator? Now, because you have moles of sulfuric acid here, and you want to get rid of that unit, then down here, you're going to put 5 moles of H2SO4, right? And then up top, since you want to have as your final answer the number of moles of phosphoric acid, you're going to put 3 moles of H3PO4. And that's basically the setup. All you have to do from here is a math. And based on what I can see here, the answer is going to be 6.00 moles of H3PO4. And that's it. And that's how you solve that particular question, right? So this is a standard mole-to-mole type calculation, right? Again, you have to work with a balanced equation in order for you to solve this kind of problem, all right? Okay, any questions about this? Any questions? Any questions? Any questions? All right, moving along. Now, this is where things can be a slightly bit more challenging, because in this type of calculation, what you're going to be doing is starting off with the moles of one substance based on the reaction, based on the balance equation, and determine the mass of another substance, or vice versa, right? So let me just skip all this here and move straight to an example here, right? So in this case, it's the same equation as before, but this time they gave you, write it here, they gave you 784 grams of H3PO4, and you're asked to determine the moles of H2SO4, all right? So basically what you have to do is start off with the grams of H3PO4, and the first thing you should do is convert it to moles of H3PO4. And in order for you to do this, at this juncture here, you're going to need a conversion factor which represents the molar mass of H3PO4, right? Then the next step is where you convert the moles of phosphoric acid to moles of H2SO4. And in order for you to do that at this juncture, you're going to need a conversion factor which represents the mole ratio between the phosphoric acid and the sulfuric acid, all right? So in terms of how we actually set this up, we're going to start off with 784 grams of H3PO4. And the first step, as I said before, is that we multiply this by a conversion factor, which represents the molar mass of phosphoric acid. So what I'm going to do here is cheat a bit. Whoops, sorry. And I'm going to use my molar mass calculator. Hold on. To calculate the molar mass of phosphoric acid. Okay, calculate, let's see what I give. So 98.00 grams would be the molar mass of the phosphoric acid. So I'm going to put that down here. 98.00 grams of H3PO4 would be equal to 1 mole of H3PO4. All right. Okay, so that's the first step. And of course, this would be the arrangement because we want this to cancel out with this. All right. So up to this point, we would have determined the moles of phosphoric acid. So now we have to take it a step further, where we're going to use the mole ratio between the phosphoric acid and the sulfuric acid based on their coefficients in a balanced equation. So we want to get rid of the moles of H3PO4 as a unit because we want to end up with moles of sulfuric acid. So the question now becomes, at this juncture, what goes up top as a numerator and what goes down here as a denominator? And the answer, of course, would be that you'd put 3 moles of H3PO4 down here as a denominator, and upstairs above, you're going to put 5 moles of H2SO4 as the numerator, so that this unit will cancel out with that unit. So the only unit remaining would be the moles of H2SO4. So of course we have to do our number crunching. So you're going to get 784 divided by 98, then multiply by 5, and then divide by 3. And according to my calculations, and please folks, please do these calculations along with me because I can be wrong. I'm subject to error. So let me do this again just to make sure. 784 divided by 98 times 5 divided by 3. Okay, so I got 13.3 moles of sulfuric acid as the answer. All right. Any questions? Any questions? Any questions? Any questions out there in Zoom? Any questions out there? Okay, I'll take your silence to mean you understand everything I'm talking about. All right, so let's talk about this example. So let's see if you guys can do this one based on what we have done before. Now, in this case, it's kind of like the reverse because, well, they gave you a balanced equation, they gave you the moles of one substance, and they're asking for you to determine the mass of another substance involved in the reaction. Okay, so let me hear what you guys think. How would you tackle this particular problem? Basically, they gave you 12, why is this thing not writing? 12.0 moles of ammonia, and they're asking for the grams of hydrogen that would react to form that much ammonia. All right, so any ideas? Any ideas? Okay, hold on. So you're saying start off with 12. Shoot. What is this thing? Okay, start off with 12.0 moles of NH3. Okay. 1 mole of NH3 at top. You sure about that?
You would put 2 NH3 on the bottom as a denominator.
Okay, so somebody out there in Zoom was saying that took 2 moles of NH3 as a denominator, which I agree with. And the reason why I agree with that, because you want to get rid of this, right? Okay, and what goes up top? 3 what? Moles of hydrogen. Very good. All right. Then what? Because remember, the question is asking for the mass in grams of hydrogen. So we need another conversion factor here, right? So the question is, what goes up top and what goes below in that conversion factor? Ah.
One mole of H2 would go as the denominator.
Okay, so 1 mole of hydrogen would go down below as the denominator. And what goes up here?
The molar mass.
The molar mass. So of course, hydrogen, there are 2 atoms per molecule. The molar mass of one is 1.008. So for H2, it's going to be 2.016 grams of hydrogen. And that's a setup. So let's do the number crunching. 12 times 3 divided by 2 times 2.016. And according to my calculations, this works out to be equal to 36.3. I hope I'm doing this right. Grams of hydrogen. Let me recheck this. 12 times 3 divided by 2 times 2.016. Okay, that's what I got. 36.3 grams of hydrogen. All right. Any questions? Any questions? Any questions about this? All right. Now we're going to step up the level of difficulty again slightly more, because now we're going to look at situations where balanced equation, let's say you have that, and you're given a mass of one substance, how you determine the mass of another substance involved as a reactant or product in a reaction. So let me just skip all this right here and go directly to this example. And in this example, same equation as the one that we just did, but this time they gave us the mass of hydrogen and they're asking for the mass of ammonia that is formed, all right? So basically, to summarize, you're given 112 grams of H2, and you're asked to determine the mass in grams of NH3, all right? So the first thing you do is you get the grams of hydrogen, which is given. You convert that to moles of hydrogen, right? Because again, that's what we have to do when it comes to stoichiometric type problem. You have to find the moles of one substance for which the information is given. In this case, the information given is the grams. You have to convert it to moles. And then, so here, you're going to need a molar mass of hydrogen to do that. And then to get from the moles of hydrogen, we can convert that to the moles of ammonia. And for us to do that, we're going to need the mole ratio. And then now to get from moles of ammonia to grams of ammonia, you're going to need a molar mass of ammonia. Molar mass. All right? So in other words, you're going to need 3 conversion factors in series. All right? One to do the first conversion from grams to moles, the second to do the conversion from moles to moles of hydrogen to moles of ammonia, and then the third conversion factor is where you convert the moles of ammonia to grams of ammonia. So start off with the 112 grams of hydrogen, and we have to multiply by a conversion factor, which allows us to convert it to moles. So what would be the numerator and the denominator for this conversion factor? Anybody? 1 mole of hydrogen over 2.016 grams of hydrogen. Okay, very good. And then now we need to do the mole ratio between the hydrogen and the ammonia. So for this conversion factor, what goes up top and what goes below? Keeping in mind that we want to get rid of this, right? So what would go down here? 3 moles of hydrogen, and what goes up top? 2 moles of, oh, wait a minute. 2 moles of what? I'm sorry. NH3, ammonia, exactly. All right, so that goes with this. Okay, and then now the final step is where we need the molar mass to convert from the moles of ammonia to grams of ammonia. So for this conversion factor, what goes down here and what goes up top? Anybody?
One mole NH3 will go on the bottom.
1
And the
mole of
molar mass will go on top.
NH3 would go below. And what goes up top, you said?
The molar mass.
Okay, the molar mass. So what's the molar mass of ammonia? I think I can do that quickly. 3 times 1.008 for the hydrogen plus nitrogen, which is 14.01, I think it is. So according to my calculation, this would be 17.03 grams of NH3, all right? So this will cancel with that. So the final units would be grams of NH3. So let's see what the calculation would give. 112 divided by 2.016 times 2 divided by 3 times 17.03. And according to my calculations, I got 631 grams of ammonia being produced. All right. Any questions about this example? Any questions? Any questions? Okay, so I think we have done enough to at least get a start on this assignment. So for you guys out there in Zoom, let me see if I've published assignment number 9. Okay, let's see here. Okay, so I'm publishing assignment number 9 right now for you guys out there in Zoom. And I'm going to hand out copies to the class, people in class here. Take one at a time. You. And I want us to focus on questions. Give me 1 minute here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so questions 1 through 11. Now let me warn you, some of these equations are not balanced. So you all know what to do, right? Make sure you balance it first. Check the equations to make sure that they're balanced first, right? And then you can proceed to the math part of solving this problem, all right? And of course, I'm here if you have any questions. In fact, tell you what, I'm feeling generous. So let's do question number 1 together. Let me download it here. Okay, so this is question number 1, all right? Let me turn on my pen function here. Okay, so this is question number 1. They gave you the equation, and if you check the equation, you see it's balanced, right? Okay, and it says how many grams of sodium sulfate will be formed if you start with 200 grams of sodium hydroxide, all right? So you're given 200 grams of sodium hydroxide, and you're asked to find out the grams of sodium sulfate. All right? Okay, so what's the first step? What's the first step?
Convert the grams to moles.
Okay, we start off with 200 grams of sodium hydroxide, and somebody over Zoom was saying that we convert that to moles. So that would mean that we have to multiply by a conversion factor, right? So what would be in this conversion factor? What would be up top as the numerator, and what would be below? Why 2 moles? Well, the answer to that would be no, because this doesn't come into play until you do the mole to mole conversion. Right now, what we're doing is just converting to moles, right? So what do we need up top here? And what do we need down here to convert 200 grams of sodium hydroxide to moles? Anybody?
1 mole of sodium hydroxide will go on top and the molar mass will be on bottom.
Okay, so 1 mole of sodium hydroxide will go up top, and the molar mass of sodium hydroxide would go below. And let me see, 22.99 plus 16 plus 1.008 Okay, so I got 400, I'm sorry, not 400, 40.00 grams of sodium hydroxide as the molar mass, right? So this unit will cancel out with that. Okay, very good. What's the next step? What's the next step? Okay, the mole ratio. So what would go up top here and what would go down here to represent the mole ratio between the sodium hydroxide and the sodium sulfate? Sure about that? Exactly. You know why? Because you can do this. You see what I'm saying? So what goes up top here? 1 mole of sodium sulfate. Very good. All right. So what's the next step? What's the next conversion factor? What goes up top and what goes below? You have to convert from the moles of sodium sulfate to grams. So what would go down here? One mole of Na2SO4. And what goes up top? Oh, you calculated already? 140 what? 0.04? Okay, I'll take your word for it. If I get the wrong answer here, blame, what's his name? Blame him. Okay, so sodium sulfate. All right, and then we do the number crunching. So 200 divided by 40 divided by 2 times 142.04. And the answer I got, now in this case, we have to round off to 3 sig-figs because we have 3 here. So 355 grams of Na2SO4. And that's how you do that, right? And pretty much it's the same approach for all the others. For all the questions I mentioned, questions 1 through 11. So you can go ahead and do those. And of course, if you encounter any difficulty, please let me know.
I have a quick question. Will you be posting the videos to chapter 9 on Canvas?
Yeah, I forgot to publish it. In fact, let me publish it right now. Let me go to modules. Yeah, I don't know. I usually remember to publish these videos. Ooh, that's chapter 14. Wait a minute. Chapter 9. And let me just say, based on what we have done today, hold on, let me get rid of this thing here. Okay, so based on what I've covered today, I've covered these 2 videos here, stoichiometry introduction and stoichiometry example. And I'm going to leave you guys to watch these videos, limiting reactants and percent yield. Then you'll be able to do the rest of the problems in the assignment. Okay, did anybody come in late?
Yes, sir. I was a few minutes late.
Okay, so this is Mr. Baldus. Anybody else? All right.
I have a quick question.
Yes, ma'am.
It's about number 2. And the way
Okay,
I'm
hold on. Let me see if I can find it here. Number 2. Okay, yeah.
it's about how I'm rounding it off because I got 319.8 and then the rest of the
Okay, so you mean when you did the calculation for the mass of lithium nitrate,
yeah,
you got hold on, write this down. 319.
0.8 and then there's more, but I'm only rounding off to 3 sig figs, so
Okay, so if you're rounding this off to 3 sig figs, it's going to be 320 with a decimal point after the 0.
okay, thank you.
Mm-hmm. Okay, let me see. What was I doing here? Now, folks, before you leave, let me just say this. So make sure, just to remind you that your test number 2 will be available next week in the respective testing centers. So make sure you make your appointment to do that test. The deadline for that test will be next week, Friday, which is the 27th. Make sure also that you watch the rest of the videos for chapter 9 and make sure that you complete this assignment and submit it next week, Tuesday. You can submit it in person or online. And then finally, make sure you watch the videos for chapter 10. Now, chapter 10 is not a long chapter. Only 2 videos I've provided for that. So make sure you watch those videos and make sure you come prepared for the assignments for those videos, all right?
I have a quick question.
Yes, ma'am.
Oh, do you have a study guide just like you did for the chapter 1 test on your files or no?
Well, I think I have the assignment keys published already for the assignments that test will cover. Let me just check here. Because I said that the test will cover chapters, what did I say? I wrote it down here somewhere. Okay, so assignments 5, 6, and 7. And yes, so these assignments are already published. So you can go there and download them and review those.
Okay, sounds good. Thank you.
Mhm. All right, take care. Okay, I'll be signing off now. See you next class, all right?